we will start a new topic from today, that is decoder circuit. But before going to the decoder circuit, two more important circuits that we have to discuss, that is adder circuit and the subtractor circuit. So adder and subtractor are basically very useful circuit in digital electronics, and we have to use this circuit in many applications, like to build any types of circuit. So first, adder circuit. So what is adder circuit? So in digital electronics, an adder circuit is a circuit that performs the addition operations of two or more binary digits, right? So what is adder circuit? It is a digital circuit that performs addition operation of two or more binary digits. Binary bits. So basically, a circuit is a digital circuit that performs the addition operation of two or more binary bits. So there are basically two types of adder circuit in your syllabus, that is 2-bit adder circuit and 3-bit adder circuit. So what is 2-bit adder circuit? In 2-bit adder circuit, the adder circuit performs the addition operation of 2-bit binary digit, and in 3-bit adder circuit, the circuit performs the addition operation of 3-bit binary digits. So first we will see the 2-bit adder circuit. 2-bit adder circuit. So 2-bit adder circuit is generally called as half adder circuit. So this is half adder circuit. Half adder circuit. So as I told that 2-bit adder circuit means that it performs the addition operation of 2-bit binary digits. So let's think that A and B are the 2-bit binary digits. This is A and this is B, and adder circuit performs the output of sum and carry. This is sum and this is carry. So what is the truth table of half adder circuit? So if there are only 2-bit binary digits, then 4 combinations are possible. That is 0 0, 0 1, 1 0, and 1 1. 4 combinations are possible. Next, what will be the output of these inputs? So if 0 and 0 added, then sum will be 0 and carry will also be 0. If 0 and 1 is added, then sum is 1 and carry is 0. This is sum is 1 and carry is 0. And if 1 and 1 is added, then sum is 0 and carry is 1. So you can see that if 1 and 1 is added, then that means 2. So in binary, 2 means 1 0. So here 0 is sum and 1 is carry. So this is the truth table of half adder circuit. So we have to find the expressions for half adder circuit, and we will see how a half adder circuit looks like. So we will take the help of key map here. First, for A's. So for A's, we will see that this is only 2-bit key map, and this is A. This is B, so 0 1 0 1. So this is 1, this means 0 1, 0 1, this is 1, and this is 1 means 1 0, 1 0, this is 1. So A is equal to, we can write here as AB. So this is B, so A bar B plus, and this is A bar. So you can write from this table, the expression of A will be A bar B plus A bar, and that is nothing but A XOR B. So the expression for sum for a half adder circuit is A is equal to A XOR B. Now we have to find the expressions for carry part. So for carry, for C, this is the key. This is A and this is B, 0 1 and 0 1. So for carry only this output will be high, so that is 1 1 1 1. So the expression for C is equal to A B. So we can see from this chain of expressions that the expression for A for a half adder circuit is S is equal to A XOR B, and the expression for carry for a half adder circuit is carry is equal to A B. So this is the expression for a half adder circuit. If we read the circuit, then it will look like that. So you see that S is equal to A XOR B and C is equal to AB. So this is A and this is B, A and this is B. This XOR, this is S and this is A, this is B, this is AND, AB, this is C. So this is the half adder circuit, and if we take the inputs of 2-bit binary digits, then it will produce the adder output of in two ways, that is sum and a carry. Next we will see full adder circuit. So full adder circuit means basically it's a 3-bit binary digits. So it performs the operation of 3-bit binary. This is full adder circuit. So what is full adder circuit? Full adder circuit. So what is the truth table of full adder circuit? This 3-bit binary digits A, B and C, and produces the output of sum and carry. So if 3-bit binary digits is here, so 8 combinations are possible: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. 8 combinations is possible. So now we have to find the output from sum and carry. So this is 0 and this is 0, this is 1 and this is 0, this is 1, this is 0, and this is 1 plus 1 means 0, 0 plus 0 means 0, and this is 1. So this is 1, 0, and this is 1 plus 0 means 1, 1 plus 1 means 0, this is 0, this is 1, and this is also 1 plus 0 means 1, 1 plus 1 means 0, and 1. 1 plus 1 means 0, 0 plus 1 means 1, and carry 1. So this will be the output for a full adder circuit, but 3-bit that performs the operation of 3-bit binary digits. So now we have to find the expressions for this full adder circuit. So what will be the expressions? So if we take the kernel, then for S, this is AB and this is C. So 0 1 and this will be 0 0 0 1. Zero 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 one. So these 4 combinations will be possible. So for S, what will be the kernel? This is the kernel. So this is AB and this is C. So this is 0 1 and this is 0 0 0 1 1 0 1 1 0 0 0 1 1 2 1 0. So these are the gray code. So if we find the gray code of 0, that means 0 0. So gray code of 0 0, gray code of 0 is 0 0. So if we find the gray code of 1, that is 0 1. So what is the gray code of 0 1? So 0 will be here, and that is 0 plus 1 is 1. What is the gray code of 2? 2. The gray code of 2 is, so 2 means 1 0. That is 1, and that is 1 plus 0 is 1. So what is the gray code of 3? 3 means 1 1. That is 1 and that is 1, and 1 plus 1 is 0. This is the record of 0, 1, 2, 3 that will be put in the kmap. You can see this from here. So what will be the expressions for S? This is what? So 0, 0, 1, 0, 0, 1. This will be 1, 0, 1, 0, 0, 1, 0. This will be 1, 1, 0, 0, 1, 0, 0. This will be 1 and 1, 1, 1, 1, 1, 1. This will be the 1. So these four are the possible outputs, high outputs. So no group can be possible here. So what will the expression for S? S is equal to formula. This is A bar B C bar plus this is A B bar C bar plus this is A bar B bar C plus this is A B C, right? So if we substitute this, so this is A bar B C bar plus A B bar C bar. If we take common of C bar here, that is A bar B plus A B bar plus if we take common of C here, that is A B plus A bar B bar, right? So this is C bar into A XOR B plus C into A XOR B whole bar. So what is this? This is XOR gate, AB plus A bar B bar. So XOR gate means the complement of XOR gate. So if we can write from this that A XOR B the complement, A XOR B or complement. So this is C bar dot A XOR B plus C dot A XOR B or complement. So that is nothing but the A XOR B XOR C. So this will be the expression for full adder circuit. A is equal to A XOR B XOR C. So if we don't have any time, we don't have much time to build the K-map, and from this K-map with the expressions, then we have to write the expressions from this truth table also. That if we consider 0 as complement and if we consider 1 as true value of the variable, then you can see from here that is in which cases the S is equal to 1, it produces the high output. You can see from here that this is 1, so this is A bar B bar C. A bar B bar C. So you can see from here that this is A bar B bar C, right? So next high output is 1. So this is A bar, 0 means complement, A bar B and C bar. So this is A bar B and C bar. So next S is equal to 1 here. So this is A B bar C bar. So see here from that A B bar C bar. And next this is 1, that is A B and C. A B C. So if we don't have any time to build the K-map, then we have to write the expressions from truth table also. It's very easy in case. So what is the carry expressions? C is equal to, you can see from truth table that we don't need to make the K-map. So C is equal to, this is A bar, so this is A bar, this is B and C. So next this is 1, this is the higher output, so this is A B bar C plus A B bar C plus A B C bar, and this is 1, so A B C. This one, so plus A B C. So if we take common from here that C, so this is C A bar B plus A B bar plus if we take common AB from here, that is AB means C plus C bar. So what is this is A bar B plus A bar means A XOR B. So this is C into A XOR B plus A, because C plus C bar is always equal to 1. So we can find, we have found the expressions for sum and carry for full adder circuit. Now we will see the circuit of how full adder circuit looks like. So what will be the expressions for sum for full adder circuit? So sum is equal to A XOR B XOR C, and carry is equal to C dot A XOR B plus AB. Now we will see the circuit. So this is A, this is B, and this is C. So this is A XOR B, A XOR B, A XOR B XOR C. So this is C, and this is A XOR B XOR C. Right? This will be the sum. And next C is equal to C into A XOR B. This is A XOR B, and this is C. C into A XOR B, plus AB. This is A and this is B. So this is C into A or B plus AB plus A. This is the whole. So this is the logic circuit of full adder circuit. If we give the 3 input binary digit to here, then it will produce the output sum and carry. So if you see the block diagram of half adder circuit, this is A, B. Sorry, this is A, this is B, and this will be the half adder circuit here. Half adder. Then it will produce the output sum and carry. And if we give the 3 input binary digit, 3 binary digits A, B and C here to a full adder circuit, then it will produce the output sum and carry. So this is the adder circuit. So next we will see the subtractor circuit. So now we will discuss about the subtractor circuit. So what is subtractor circuit? Subtractor circuit is basically a circuit that performs the subtraction operations. So like adder circuit, there are 2 types of subtractor circuit in digital electronics that are basically more important. That is half subtractor circuit that performs the operations of 2 binary digits, 2-bit binary digits, and full subtractor circuit that performs the subtraction operation of 3-bit binary digits. So what is half subtractor circuit? This is half subtractor circuit. This is the truth table of half subtractor circuit. There are 2 bit binary digits A and B input. So this is 4 combinations possible, and there are possible 2 outputs is there, that is division and borrow. So when we perform the operations of subtractions, then 2 types of output will be possible, that is division and another is borrow, because sometimes we have to take the borrow from our previous digits. So this is division and borrow. So 4 combinations possible: 0, 0, 0, 1, 1, 0 and 1, 1. So this is the division and borrow. So if 0, 0 is input, then the division is 0 and borrow is 0. If 0 is input, then we have to take and borrow. So that is borrow is 1 and division is 1. If 1 and 0 is the input, then division is 1 and borrow is 0. If 1 and 1 is input, then division is 0 and borrow is 0. So this is the truth table of half subtractor circuit. So what will be the expressions for half subtractor circuit? This is D. So D is equal, you can see from here that this is A bar B, and this is B bar. So this is nothing but the A's or BI. So D is equal to A's or BI. So this is the expressions for division. So what will be the expression for B? So here we can see B is equal to A bar B, A bar BI. So this is A bar BI. So this is the expressions for B. Now how the half subtractor circuit looks like? So this is A. We can write this as A and this is B. So D is equal to A XOR BI. So this is A XOR BI. And this is D, and B is equal to A bar, this is A bar, and BI, this is BI. So this is A XOR B, this is D, and this is A bar B, this is B. So this is the half subtractor circuit. So you can see from here that the block diagram of half subtractor circuit, if A and BI are the 2 inputs, then this is the half subtractor circuit, and division and borrow will be the 2 outputs. Now we will see about the full subtractor circuit. So full subtractor circuit basically performs the subtraction operation of 3 bit binary digits. So here this is the 3 bit binary digits A, B, I, and A, B input and C. So 8 combinations possible. We will see the 0, 0, 0 to 1 and 1, and this will be the division and borrow as per the subtraction operation. We will see the truth table of full subtractor circuit. This is division and borrow. So what will be the expressions for division here? So division means this is 1. So this is A bar, B bar, C, and this is A bar, B, I, and C bar. And this next this is A, B bar, C bar. Next this is A, B, and C. So if we take the formula of A bar here from here, that is B bar C plus B C bar, and plus if we take the formula from A here, then this is B bar C bar plus B C. So this is nothing but A bar into B dot C, and this is A plus A dot B XOR C whole bar, because we will see that BC plus B bar C bar is the XOR operations, and that is the complement of XOR operations. So this is A B XOR C whole complement. So this is nothing but D is equal to A XOR B XOR C, because this is A bar B XOR C plus A B Z C whole bar. So that is B is equal to A Z B Z C. Now what will the expression for borrow B here? So B is equal to, we can see from here that this is A bar B bar C, and this is A bar. This is A bar B C bar. Next this is A bar B C. Next this is A B and C. So if we take common from C here, and this is from C. If we take common from A bar B bar C and A B C, if we take common from C from these two terms, that this comes A bar B bar plus A B, and if we take common A bar B from these two terms, this comes C plus C bar. So C plus C bar is also equal to 1. So you can write B is equal to C into A bar B whole bar, that is A bar B bar plus A B plus A bar B. So this is the expression for borrow here. So how the full subtractor circuit looks like, we'll see. So we can see that B is equal to A XOR B. So this is A, this is B I, and this is C. So D is equal to A XOR B XOR C. This is A XOR B, and this is A XOR B XOR C. So this is D, and what is D? D is equal to C dot A XOR B whole bar. So this is A XOR B, its complement, and into C. So this is C. So C dot A XOR B whole bar plus A bar B. So this is plus A bar B. This is A bar. This is B. A bar and B. And this will be added. This is B. So we can see from there that B is equal to A XOR B XOR C, and B is equal to C. This is C dot A XOR B whole bar, C dot A XOR B whole bar plus A bar B. So this is the circuit for full subtractor. So in this way we can see the adder circuit and subtractor circuit. From the next lecture we will start a new topic that I told before, that is decoder circuit. So I will give you an assignment that implement full adder and full subtractor circuit using 2 half adder and 2 half subtractor circuit. So basically you have to implement the full adder circuit using 2 half adder circuit, and you have to implement a full subtractor circuit using the 2 half subtractor circuit. This is your assignment. You will try it in your home and put your comments, your answer to your comments, and if you find any problem, then I will discuss it in the next lecture. Thank you for watching.